Today we are here in the day 2 of Introduction to Coordination Chemistry. In the last class we saw that there are basically two parts in a coordination compound. They are the coordination sphere and the ionization sphere. Today we will be discussing about this in details. For that we need to know a theory, that is the Werner's theory of coordination compounds. According to this theory, the central metals of coordination compound has two types of valencies. That is the primary valency, which is given by the oxidation number of the central metal, and the secondary valency, which is given by the coordination number of the central metal. Let us study about these valencies one by one. At first, the primary valency. As the primary valency indicates the oxidation number, let us understand what is oxidation number. Oxidation number is the number of electrons lost or gained by an element while forming a compound. To be clear, let us take the formation of sodium chloride. To form this compound, one sodium atom and one chlorine atom is required. During the formation, the sodium atom loses its outermost electron, which is accepted by the chlorine atom in its outermost shell. As the electron is negatively charged entity, the sodium atom, after losing one electron, becomes Na+, that is a positively charged ion with charge of +1. Therefore, its oxidation number is +1. In the case of chlorine, as it gains one electron, which is negatively charged entity, it becomes Cl-, that is a negatively charged ion with charge of -1. Therefore, its oxidation number is -1. After understanding what is oxidation number, let us learn how to calculate oxidation numbers of elements and compounds. For calculating oxidation number, we have certain rules. The first rule says that oxidation number of a free element is taken to be 0. Now, what is a free element? An element not bonded to any other element is called a free element. For better understanding, let us take few examples. In the first example, we take carbon. Here, as carbon is not bonded to any other element, it has an oxidation number of 0. Similarly, in the next example, iron atom is not bonded to any other element and hence has an oxidation number of 0. In the third example, we are taking a chlorine molecule. You may be thinking that here two chlorine atoms are bonded together, so how it can be a free element? The answer is that the two atoms here are of the same element and not bonded to atoms of any other element. Hence, we can consider it as a free element and its oxidation number is 0. One more such example is that of the oxygen molecule. Here, two oxygen atoms are bonded together and being a free element, its oxidation number is 0. The second rule says that in general the oxidation number of hydrogen is +1. For example, in ammonia there are 3 hydrogen atoms and each hydrogen has an oxidation number of +1. But in ionic hydrides, oxidation number of hydrogen is -1. For example, in sodium hydride, oxidation number of hydrogen is -1. And sodium hydride is an ionic hydride because its components are in the form of ions. Now let us go to rule number 3. This rule says that in general the oxidation number of a compound is -2. For example, in KMnO4, each of the 4 oxygen atoms has oxidation number -2. But in case of peroxides, the oxidation number of oxygen is -1. Now, what are peroxides? These are a group of compounds with a peroxy linkage, that is a oxygen-oxygen bond with 2 substituent groups, which can be any alkyl, aryl or hydrogen. For example, in sodium peroxide, the oxidation number of each of the 2 oxygen atoms are -1. Again, in superoxides, that is the oxides which contains O2- ions, the oxygen has an oxidation number of -1/2. For example, in potassium superoxide, the oxidation number of oxygen is -1/2. And in compounds where oxygen is bonded to fluorine, the oxidation number of oxygen is a positive number. For example, in oxygen difluorine, oxidation number of oxygen is +2. Now let us go to the fourth rule. It says that the oxidation number of ions composed of only one atom is equal to the charge on the ion. For example, let us consider Na+. Here, as you can see, Na+ is an ion with only one atom, that is the sodium. So its oxidation number will be equal to its charge, and in this case it is +1. Let us consider another example. Here the ion O2- has a single atom, that is oxygen, and its charge is -2. Hence its oxidation number is also -2. Next, let us go to rule number 5. It says then halogens have oxidation number -1. For example, the oxidation number of chlorine in lithium chloride is -1. But again, when chlorine, bromine and iodine combines with oxygen, then the oxidation number is always positive. For example, the oxidation number of chlorine in HOCl is +1. Then let us go to the rule number 6. It says that oxidation number of alkali metals, that is the elements of group number 1, is +1. For example, oxidation number of sodium in sodium bicarbonate is +1. And the oxidation number of alkaline earth metals, that is the elements of group number 2 in the periodic table, is +2. For example, the oxidation number of calcium in calcium chloride is +2. Then let us go to the rule number 7. It says that the algebraic sum of the oxidation number of all the atoms in a compound must be 0. Let us see an example. In the molecule of water, there are two elements, hydrogen and oxygen. As we have already seen, oxidation number of hydrogen is +1 and oxidation number of oxygen is -2. Now, we need to add up the oxidation numbers of the two hydrogen atoms and one oxygen atom present in the molecule. Here, we are multiplying the oxidation number of hydrogen, that is +1, with 2 because there are two atoms of hydrogen, and we are multiplying oxidation number of oxygen, that is -2, with 1 because there is only one oxygen atom. Now after mathematical calculations, we would get a result 0, and this proves the rule. Next, we will go to rule number 8. It says that in polyatomic ion, the algebraic sum of all the oxidation numbers of atoms of the ion must equal the charge on the ion. Here the polyatomic ion means an ion which has more than one type of atom. Let us see an example. In the ion OH-, there are two types of atoms, that is one atom of oxygen and one atom of hydrogen. So it is a polyatomic ion. We know that the oxidation number of oxygen atom is -2 and that of hydrogen atom is +1. Now let us add up the oxidation numbers of the atoms of the ion. By mathematical calculation, we get the result -1, which is same as the charge on the ion, and this is in accordance with what the rule number 8 says. So these were the rules for calculating oxidation numbers. Now let us see an example where we can find an unknown oxidation number of an element in a compound by using the rules. For that, let us find the oxidation number of manganese in KMnO4. From these rules, we know that the oxidation number of potassium is +1 and that of oxygen is -2. And also from the rules, we know that the sum of the oxidation number of all the atoms in the compound will give us a result of 0. Hence, the sum of oxidation number of one potassium atom plus the oxidation number of one manganese atom plus the oxidation number of 4 oxygen atoms should be equal to 0. Now, by mathematical calculation, we get the unknown oxidation number of manganese atom as +7. That is how we can find out an unknown oxidation number in a compound. Now that we understood the oxidation number, that is the primary valency, let us move forward to understand what is coordination number, that is secondary valency. It is the number of atoms or ions directly surrounding, that is directly bonded to the central atom. For example, in a complex ion, the iron atom, which is the central metal atom, is bonded to 6 cyanide ions. Then its coordination number will be 6. In another example, if we consider a platinum as the central metal atom, which is bonded to 4 chloride ions, then its coordination number will be 4. Now, let us clear our concept about the primary and secondary valency by understanding them with examples. So, here is an example of coordination compound. In this compound, let us at first find out the coordination number, that is the secondary valency. As we have already studied, the portion of the compound which is inside the square bracket is called the coordination sphere. Here we have the cobalt as the central metal atom, which is bonded to 6 ammonia atoms, actually molecules. It can be shown in structure as this. Since the central atom here is bonded to 6 ligands, its coordination number, that is the secondary valency, is 6. The secondary valency of a metal is said to be directional because the direction of bonds formed depend on it and hence denotes the structure of the compound. Then let us find the oxidation number or the primary valency of the central metal. From the rules of oxidation number, we know that the sum of oxidation numbers of all the atoms in a compound is equal to 0. So in this case, oxidation number of cobalt plus oxidation number of ammonia plus oxidation number of chlorine should be equal to 0. Here the oxidation number of cobalt is unknown and to be calculated. The oxidation number of ammonia is 0 because ammonia being a neutral molecule, the sum of the oxidation numbers of its atoms will be 0, and we are multiplying the oxidation number of chlorine, that is -1, with 3 because there are 3 chlorine atoms. Then by mathematical calculation we get the oxidation number of cobalt as +3. As we can see that this oxidation number of cobalt here is only because of the 3 chlorine atoms present outside the coordination sphere. Hence we can say that the primary valency is satisfied by these 3 chlorine atoms only. In structure, the primary valency can be shown by using dotted lines, which is 3 in this case. The primary valencies are non-directional, that is, they do not give structure to the compound. Now let us go to another example. In this compound, the coordination sphere has cobalt as a central metal, which is bonded to 4 ammonia and 2 chlorine atoms. Let us see it on structure. Here the cobalt is bonded directly by coordinate bonds with 4 ammonia and 2 chlorine atoms. Hence, its secondary valency will be 6. Now let us find out the oxidation number or the primary valency. According to the rules, the oxidation number of cobalt plus the oxidation number of the ammonia molecules plus the oxidation number of all the chlorine atoms will be equal to 0. And by mathematical calculation, we get the oxidation number or primary valency of cobalt as +3. Again, in the structure, we can show this by dotted lines. Here we can see that 1 chlorine atom is only bonded with dotted lines. This chlorine satisfies only the primary valency and hence is written outside the coordination sphere. The other 2 chlorine atoms has both dotted lines and solid lines. It means that these 2 chlorine atoms satisfy primary as well as secondary valency and is written inside the coordination sphere. In whole, the primary valency here is 3. Now, let us summarize the whole concept of Werner's theory. According to this theory, in a coordination compound, there is a coordination sphere written inside the square brackets and an ionization sphere. In the coordination sphere, there is a central metal which is bonded with coordinate bonds to ligands. The number of such coordinate bonds gives us the coordination number or the secondary valency of the central metal. The atoms in the ionization sphere gives the oxidation number or primary valency of the central metal. Some atoms or molecules inside the coordination sphere can also contribute to the primary valency. But during ionization, only the atoms of the ionization sphere gets ionized, and whatever is inside the coordination sphere remains as one complex ion. To be clear, let us see the ionization of this very compound. It will get ionized to one complex ion and 2 chlorine ions, as there are 2 chlorines in the ionization sphere. So, here we end our today's class. Thank you.